Alright, hey guys, for this week I'm supposed to help with number 68 on chapter 33, and the problem is set up with this thing here. A conducting bar of length L and mass M rests at the left end of the two frictionless rails of length D, and a uniform magnetic field of strength B points upwards. Alright, so for part A, we're supposed to find out if this mass were to be going to the right, which way would the current have to be going inside of the mass? Would it have to be going into the paper or out of the paper? And for this we just use our right hand rule, so right hand. Our thumb is the force, which is just the direction, so this way. And then our middle finger is the B field, sorry about this. And then, so that means our pointer finger is going to be the current, which is into the paper. It's kind of hard to see, but yeah, so yeah, middle finger up, force this way into the paper, so that means the current has to be going into the paper. So yeah. Alright, so for part B, we're supposed to assume that there is a current going into the paper, causing this bar to move to the right. And we're supposed to find an expression for the final velocity as this leaves the rails. So first things first, we start out with the force, and F equals the current times the length crossed with the magnetic field B. And so then we get this F equals IL cross B. And right, so first thing, I guess we get, or simplify the cross part. So we get the current times the length times the magnetic field times sine theta. But here we can see that the magnetic field is perpendicular to the current, the direction of the current. So BI, it's perpendicular, 90, so sine 90 equals 1. So then we are left with F equals the current times the length times the magnetic field. And then using Newton's second law, we can remember that F equals ma, and then set these two equal to each other. So ma equals ILB, and then we just solve for a, the acceleration, by dividing the mass on both sides. So now we have an expression to find the acceleration, but we want to find the final velocity, so we have to use another one of our really old equations from previous classes, and that's the final velocity squared equals the initial velocity squared plus 2ax. We know this starts from rest, so that means the initial velocity equals 0. And for x here, or we're not using x here, we're using d, the distance. So yeah, so we get v squared equals 2ad, and then we already solved for a in terms of these values. So if we substitute a, we get 2ILBD over m, and then you get the final velocity, and just take the square root of both sides, so you get v equals the square root of 2 times the current times the length times the magnetic field times the distance over the mass, and that's this, we take the square root of that. And that is an expression for the final velocity. Alright.